Alright guys, here we go. So we're going to review that second to last question we did yesterday because I wanted to go over it more detailed. So it's the same question. You don't have to write these notes down because you kind of already have them, but if you wanted to redo it again, that's fine. So we're using two limits from notes 2, and these are the limits we are using. So how are they going to look when we start plugging them in? They're not going to look exactly like this. They're going to look like, it's going to look like this. Limit as h approaches 0 of 1 minus cosine h over h. That equals 0. And then this one you guys already know, it's going to look like this. Limit as h approaches 0 of sine h over h, and that equals 1. Those are given. This is given. And this is given. Are we still okay? Nothing crazy. I haven't done anything yet. Cool? Alright. So what do I need? I'm looking at this, and it looks like I need f of pi over 6. That's what f of c is. So f of pi over 6 is cosine of pi over 6. And cosine of pi over 6 is? Yes, square root of 3 over 2. And that's it. Alright, next. I need f of pi over 6 plus h. We still okay? That is cosine of pi over 6 plus h. And remember yesterday we used this property, and I'll write it over here. Cosine a plus b. We said that was cosine a, cosine b, and then we said minus sine a, sine b. Are we still okay, guys? Alright, so this is expanding it using that on the top. Well, I know you can't see it, right? But cosine pi over 6 cosine h minus sine pi over 6 sine h. Are we still okay, guys? Alright, let's simplify that really quick before we continue. So cosine pi over 6 is square root of 3 over 2 cosine h minus sine of pi over 6 is 1/2. And then sine h. Are we okay so far? Okay, here comes the moment of truth. I am now going to start evaluating the difference quotient with an h on it. So I'm going to write limit, and I left the whole page blank so we can use the whole page here. Limit as h approaches 0 of f of pi over 6 plus h minus f of pi over 6 all over h is equal to, and I'm going to write this on top first. So square root of 3 over 2 cosine h minus 1/2 sine h. That's what f of pi over 6 plus h is. Minus square root of 3 over 2. All this is over h. And there's a limit in front of that equal sign that I didn't write. But limit as h approaches 0. This right, yes, this right here is the f of pi over 6 plus h. This here is from the f of pi over 6. And the word limit is still on top. Yes, ask.
Wait, okay. So just to clarify, the f of pi over 6 is from the minus f of c, right?
Yeah, but they told me right here what c is. What was the c value? Yeah, I wanted to keep the formatting that UH asks on their question for trig limits number 5, question 10. And this is the formatting that they use.
So you kind of just split that.
Yeah, I just plugged in a pi over 6 in here and a pi over 6 right there. And I did this, I found that, and I found that, and now I'm putting it together. And the last step I think I wrote limit and blah, blah, blah. And then that's what that is. Any other questions, guys? We're good over here? We're good over there? Okay. So now, here's what we're going to do. I'm going to move that square root of 3 over 2. I want to put it in the middle term, and I want to move that 1/2 sine h to the right. So I'm still writing the word limit. Limit as h approaches 0. And I'm going to write square root of 3 over 2 cosine h minus square root of 3 over 2 minus, they keep the sign because I haven't moved it anywhere. All I did was put it in the middle instead of like moving it to the other side of an equal sign or something. Are we still okay? Okay. So now I'm going to group these two. So what am I going to do? Like this. Don't worry, I'm going to go slow, guys. Limit as h approaches 0. And I'm going to do a giant parenthesis. I'm going to factor out a negative square root of 3 over 2. Why? Because I want it to look like this one. I want to have a positive 1. And at the moment, if I factor out a square root of 3 over 2, I get a negative 1. Actually, I should have probably rewritten the cosine, but that's fine. Are we okay? Yeah. What I mean by I should have rewritten it, this, by the way, I could have also said this. Limit as x approaches 0 of cosine x minus 1 over x. That's also 0. But I didn't do that, so I'm just going to fix my error by factoring out a negative 1. Cool? Okay. Negative square root of 3 over 2. When I do that, I'm going to write this one first. 1 minus cosine h minus 1/2 sine h, and all this is still over h, like so. Are we still okay? Okay. Can I use my properties of limits and do this? I'm going to write limit as h approaches 0, negative square root of 3 over 2, 1 minus cosine h over h minus limit as h approaches 0, 1/2 sine h over h. Can I do that? Yes. All I did was just split it up. Yes. Yeah, I see it. It's all over h. A plus b over c is the same thing as a over c plus b over c. This is a side note. I don't want you guys to think like, where's this coming from? Are we still okay, guys? This square root of 3 over 2 is just a constant. I can rewrite that and put it in the front. Same thing with that half. Just to make it neater. If you don't like that, you can leave it alone. But just to make it neater. Negative square root of 3 over 2. Limit as h approaches 0 of 1 minus cosine h over h. See, it looks a lot cleaner now. Minus 1/2 limit as h approaches 0 of sine h over h. Are we okay? Yes. Yeah, you don't, yes, you can do it without moving it over. Okay. Next, this looks a lot cleaner now. I have negative square root of 3 over 2. That's a 3. All this right here is just what? No, it's just 0. So I have, where did it go? Oh, right here. 0 minus 1/2. And all this right here is just what? 1. So my final answer is just, no. Negative 1/2. Yes. Yeah, we're solving the limit. Once you evaluate the limit, you don't have to write the word limit anymore. Limit as h approaches 0 of sine h over h is 1. You know what I mean? Just like limit as x approaches 0 of sine x over x is 1. Cool? How do we feel, guys?
I understand, but it's
Yeah, no, you're gonna need. Yeah, that's what you're gonna need for the last question on trig limits, question 5, and that's what you're gonna need for the circuit for one of the questions. Yes, ma'am. Here. That's a 3 there. Okay. All right. We're going to skip the sandwich theorem momentarily. We'll come back to it. We're going to come back to it, guys, because we need that for the activity. I think I already extended the activity for until tomorrow. So I should never have passed that activity out. So I'm sorry. All right. So let's look at this limit. So a lot of you are getting these type of questions incorrect. So we're going to talk about it. Limit as x approaches infinity of 2 plus 3e to the 1 over x. What is that limit? So how do we evaluate it? On the side, I'm going to write limit as x approaches infinity of 1 over x. I'm just evaluating that exponent. 1 divided by a huge number is 0. Does everyone agree? Perfect. So if 1 divided by a huge number, that's the only tackle that I really have over here, guys. So then that means as x approaches infinity, I can write this as 2. There's no x there. Plus 3 e to the 0. And if this were an AP exam, I think I would, I would not want you to leave it like that, but you can. And that would be counted correct if this was the answer. We're better than that, I think, and we can do better than that. E raised to the 0 is what? 1. And 3 times 1 is 3. And then finally we just add the 2. Notice I don't write the word limit anymore because I'm already evaluating it. What is 3 plus 2? And there it is. So this limit, as x approaches infinity, of 2 plus 3 e to the 1 over x is nothing more than 5. Yes. From e to the 0. E to the 0 is equal to 1. Any other question, guys? Do you guys have any question that you want to make up? Just give me a random one. Nope. If it were negative, it would still be the same answer. Yes. It's the same answer if I were to approach negative infinity, because it's 1 divided by a huge magnitude, which is 0, regardless of whether it's positive or negative. Yes, what's up?
I don't have a specific question in mind, but if it's asking you for what the horizontal asymptote is all,
Okay.
and then it's something either like this or even like the ones that I was having were like this, and on the outside you do like minus e to the x or something, and so that I didn't know like whether I should pay attention to the inside or the outside.
Well, you got to pay attention to all of it.
Yeah.
When it comes to horizontal asymptotes, that is connected to end behavior, which is connected to as x approaches infinity and negative infinity. So a lot of times the most common mistake is that we as teachers only look at one direction, but we got to look at both positive infinity and negative infinity. And you brought up a really good question. In 2008, there was a College Board rarely ever does this, but in 2008, they actually took out a question because, remember, everything is mathematical, like all the data. The ones were getting higher than the 5s. And they can't have that, right? We can't have that. So College Board scrapped it and gave all the high school teachers a stark warning. They literally did. They're like, this is a valid question. Teachers should evaluate positive and negative infinity, because they asked for horizontal asymptote. So I bet you that they, were like telling every single high school teacher, evaluate both directions. So who knows? The professor was probably mad.
Yeah.
Well, what did I say? What? Yeah, the ones, the breakdown of, remember that question that I told you where I told you like the 3s got 67% correct, the 4s got this, the 5s got this. In 2008, the percentage of ones that were getting that specific question correct was higher than the 5s. And it was one of these. It was a horizontal asymptote. And because of that, they were like, bad question, out. Because they should...
Wait a sec, no, wait, that doesn't seem right.
Yeah.
That doesn't seem
No.
You're gonna run this question on that.
Okay. Is the 1 over x plus 2 all part of the exponent?
Yeah.
Okay. So here we go, guys. We got a question from Delty, and we got this one. Limit as x approaches infinity of 3e to the 1 over x plus 2. I like it. where all this is part of your exponent. So before I continue, let me go ahead and write a line here. Bless you. So in blue, I'm just going to evaluate the exponent part. Limit as x approaches infinity of 1 over x plus 2. Well, 1 divided by a huge number is 0, but 0 plus 2? 2. So now this turns to 3e to the what power? 2. And you can probably type that in there and it'll give you the credit. 3e squared. Cool. Yes. Well, it depends. It depends what you know, yeah, what they're asking for, what type of behavior. What's up? Now you need a calculator, unless you know what the value of e is. 1 point, blah, 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 goes forever. That's it for that one. You can't evaluate it any further. What's up?
Wait, so how would you type that?
Just that. You just go 3e squared.
If they're asking for the horizontal asymptote.
That is my horizontal asymptote. If they're asking for the horizontal asymptote, you got to write y equals 3e squared. I'm pretty sure they're making you type y equals. Okay. Because it's a horizontal asymptote. That's your end behavior. That's the value that y converges to. Does that make sense, guys? Any other questions, guys? Ask. 3e squared. What's up? What's up, Taylor? Yeah, give me another one.
So we should just find the horizontal asymptotes of the function and then f(x) equals 1 over 2, and then in parentheses 2x cubed minus 6. And then that bit was in parentheses. And then times e to the negative x.
Okay, we can do that one. You guys ready for this one? This one says I want my horizontal asymptotes. So I want to check both behaviors, negative infinity and positive infinity. Before I continue, does everyone know how e to the negative x looks like? It's a graph. Let me show you what that graph looks like. E to the negative x looks like this. Cool? Because it's e to the negative x. Yay or nay? All right. So now, let's see. Okay, I think we're ready now. So now, let's do limit as x approaches positive infinity of that function. Well, my ocean is a 2x cubed, so that's just positive infinity there. But notice that this guy is approaching 0, so it doesn't matter how big that 2x cubed is, that e to the negative x, because I'm approaching practically 0, any number times 0 is going to be 0. So this has 0 as 1. Yes. E to the negative x, I'll put this here on the side. The limit as x approaches infinity of e to the negative x is 0. So any number, who cares what that number is, any number times 0 is going to be 0. So my limit, my horizontal asymptote is y equals 0. I can't approach negative infinity because that would be positive infinity times negative infinity, which would be negative infinity. But I can approach positive infinity, which would be 0. So this has one horizontal asymptote. Did I answer your question, Taylor? And then ask, where the point of confusion? You would, but I already noticed that if I approach negative infinity, the output for e to the negative x is infinity. So I see infinity times infinity, which would have been infinity. Well, I see negative infinity times infinity. Yeah, I'll do it. I'll do it in green. Limit as x approaches negative infinity for this function. Now notice what my ocean is on that parenthesis. It's 2x cubed. How does 2x cubed look like? Like this. Who cares about that minus 6? That's just a vertical shift down 6. Cool? So I have negative infinity because I'm going down forever times positive infinity. Now if we were subtracting, that might maybe be something, but right now we're multiplying. Negative infinity times positive infinity is just going to give me negative infinity. Does that make sense? So we're thinking about the y values. If I went to both directions and I did not converge on any number, no horizontal asymptotes. But I did converge. As x approaches infinity, I did converge at that 0. Do you know what I mean? Don't worry, I see you guys.
Whenever e to the negative x is always 0.
If I approach positive infinity, yes.
What if you approach?
E to the negative x, if you approach negative infinity, is positive infinity. So that's not. Yeah. What do you guys think? Okay, what's up? This guy? As I approach negative infinity on the 2x cubed, here it is. I'm approaching negative infinity. The y values are negative big numbers. So that's negative infinity. So negative infinity times a positive infinity is an even bigger infinity, but in the negative direction. Because negative times a positive is a negative. E to the negative x approaches big y values as x approaches negative infinity. Cool? Yes. Yeah. You want to use that shirt as a t-shirt? Sorry, miss. All right, what's up? Any other questions, guys?
I'm sure I'll have more.
Yeah, there is a safe space. You ask whatever you want to ask, miss. I mean, well, academic question, not like, why does pizza taste? It depends. Sometimes Peter Piper pizza is hit or miss. Sometimes Peter Piper pizza is the absolute best, and sometimes it tastes like cardboard. So it just depends. All right, guys. Yes.
But how do you know which one is the
Positive infinity, negative infinity, always. End behavior is when what happens as x approaches positive infinity. What happens as x approaches negative infinity. If x is approaching a big number, a big magnitude, either positive or negative, that's end behavior. So limit as x approaches positive infinity, limit as x approaches negative infinity.
But how do you know which one is your ocean versus
It depends on what type of equation you have. If you have a polynomial, the ocean is the one with the highest power. If you have an exponential, exponentials beat the polynomials all the time. If you have a logarithmic, logarithms grow very slow. So that's going to be like this.
logs don't?
Logs are at the very end. And if you go by rates of growth. Exponentials are at the top. Now there's something that grows faster than exponentials, but I don't think that's in Cal.
So if you have or for this one, if I have x plus e to the what will end up being 0.
All right, let me see. Give me your equation.
It's f of x equals
All right, guys.
x plus e to the negative 1 over x. So I know that e to the negative 1 over x will just be it'll be 0 and it'll be 1.
Yes. So we're gonna do this.
At
Limit.
that point, are you substituting the infinity until it's infinity, or is it converging on 1?
No, this one is not converging at all because of the linear aspect of it, the x plus. So if I write limit as x approaches infinity for this, while the negative 1 over x is approaching 0, so that's e to the 0, which is 1, but the infinity that I have in the front, the x that I have in the front, yeah, this is not converging to anything.
That's what I was thinking, but then I was like, wait, is the end behavior supposed to be, is it the x?
Yeah, and this one, the x is your ocean here on this one. You know what I mean? So on this one, I'm not converging to anything. The 1 over x, I mean, that's a convergent to 0, and e to the 0 is 1. But the x in the front is what's making it go haywire. You know what I mean? Does that make sense or no? Okay. Any other questions, guys, on this? Yeah, that one has no horizontal, no ha. How do we feel? All right, I think. Do you guys want to discuss the squeeze theorem now? Minus will. Trying to think of what question you had in your activity. Was it cosine x, squeeze theorem? Cosine x, right? Take out your activity real quick. From Friday. Do you have one that says sandwich theorem or squeeze theorem? Okay, what equation did I give you guys?
6 and 7. Okay, so the first one is a limit of x plus sin x over x. Okay, that's just yeah, that's
But I mean, I guess you can use the sandwich theorem for that one too. Do I say cosine x over x for any of them?
There's 1 minus cosine x.
Yeah, both. I wouldn't even use the squeeze theorem for both of those, but no, I stole that one from someone, but that author who wrote it, I wouldn't use squeeze theorem for that. But all right, let's just talk about the theory of what squeeze theorem is. So let's say I want to know. Let's say I tell you that I want to prove that limit as x approaches zero of that x approaches infinity of cosine x over x is 0. And we know that because cosine just goes between -1 and 1. And if I keep dividing by a bigger and bigger number, well, of course, I'm going to be approaching 0 because cosine is just going between -1 and 1, and I'm just dividing by bigger and bigger and bigger number. So it probably does something like that, where it wiggles to 0, and it does the same thing in the other end. Something like that. You know what I mean? All right. So here's how they would probably prove it with sandwich theorem. You write cosine x, and then you say, what's the biggest cosine x will be? 1. Did someone sigh at this? Like, 1. -1. Cosine x is between -1 and 1. The biggest cosine x will be is 1. The smallest cosine x will be is -1. Is that clear?
Yes.
Okay. If you wanted to use sandwich theorem, notice, just like a sandwich, that cosine x is in the middle. If I go divide by x, divide by x, divide by x, because that's what we're trying to prove, cosine x over x. If we can prove that the right side converges to 0, and we can prove that the left side converges to 0, then by sandwich theorem, or squeeze theorem, because we're squeezing it in, then the center one must also converge to 0. Does that make sense? So then I have an expression like 1 over x, and then I go limit as x approaches infinity of 1 over x. And I say, 1 divided by a huge number, that's 0. And then I go to the left side over here, and I go limit as x approaches infinity of -1 over x. And again, I'm still approaching -1 divided by a huge number is going to be 0. And then from there I can make a statement. I can say, hence, comma, through squeeze theorem, which is actually what it's called. You can also call it sandwich theorem, comma, limit as x approaches infinity of cosine x over x must be 0. Because it's 0 at both extremes. So if it's 0 at both extremes, then the middle one must be 0. Yes? I wrote cosine x first, like that. And I said, what's the biggest cosine x is? 1. What's the smallest cosine x is? -1. And then I just did, divide by x, divide by x, divide by x. Whatever you do to one, you do to the other. And then I evaluated this expression and evaluated that expression. Cool? What's up?
Does this work for if you have things that don't converge to 0, like converge to like 10 or...
Yes, as long as both ends converge to the same value. Now, if they don't, let's say this one converges to 10 and this one converges to 5, then we can't make a guarantee. We just know that the limit is somewhere between 5 and 10. But we can't say, what's the limit? Well, I don't know. I got one extreme at 5, one extreme at 10. But if they both converge to 10, which they did that on the AP exam 2 years ago, before the pre-pandemic, they gave one like this in the previous months. They both converged to a specific number, and that's how they found that specific limit.
So how do you tell if they'll both converge? Or do you not?
Sometimes you can tell. Sometimes they'll give you a graph, and they'll give you like, here's one graph, boom, and then here's another graph, boom, and then here's a third graph, boom. And in between all three graphs, they all share 1 point. Do you see that? So for all three of them, all three graphs as I approach, but maybe you don't have the equation for the green one. I'm just making this up because the green one's obviously the easiest curve because it's a linear line. But so maybe they give you the equation for that parabola there and that curve, and then we prove that they're both going towards that value, and then they tell us that that green value is between the big one and the small one. So by Squeeze Theorem, all three of them are converging at that same number, which is actually what the AP did 2 years ago. We don't have the math skills yet to do that one, but when we get there, we will do that one. Did I answer your question? Any other questions, guys? How do we feel? We feel okay? Hold on, guys. My neighbor texts me, and she never texts me. So what's going on? Oh, yeah. Yeah, that's all it was. I was thinking it was something important. She calls me neighbor. Yeah, she calls me. Oh no, she goes, "Happy birthday, Omad." All right, don't worry about it. Don't worry about it. It's just another day, guys. Let's keep going. Huh? Yeah, no, I told her happy birthday. All right, here we go. Ready for the definition of continuity? It's a very easy definition. The definition that you were told when you were in middle school is if you can draw the graph without lifting your pencil, it is continuous. And I think that's true for the most part. If you can draw a graph without lifting the pencil, it's continuous. Cool? All right. What's the real definition? The real definition of continuity is this. Do you guys want to read it and then tell me if it makes sense? I think that one kind of makes sense. Did that make sense, guys? Kind of? Okay, here's what it's trying to tell you in pictures. Here's a C. Limit as x approaches C from the left of this function definitely equals limit as x approaches C from the right of that same function, if I call this f. But at the moment, it's not continuous. Right now, my limit is just converging at the same y value. How do I prove that it's continuous? That if my left side equals my right side also equals the function evaluated at that x coordinate. I'll say it again. So at the moment, if I just delete the f of c part, if I just have this, that just means that I'm converging at the same y value. Do you guys agree? Yeah. Now, not only must I converge at that same y value, I must also be that y value. How am I that y value, Chav? Well, I'm approaching c, so I better be approaching f of c. Remember, f of c just means some y value.
So it just means, so that just means that there can't be a hole.
There can't be a hole. Perfect. That's all it means. So if I equal f of c, that means there it is. I plugged it in. It's nice and continuous. My left limit equals my right limit, which just so happens to also equal that value, that y value, when it's evaluated at that c value, at that x coordinate.
So was it the previous question, and it would find the limit of C, and it's not left to the right, and if there was a hole there, that means it wouldn't be continuous?
It wouldn't be continuous. But do I have a limit? Yeah. That's just not continuous because you have a hole. What's up?
But
If they connect and it says f of c, it fills in the hole. Now, if you don't see f of c and let's say I have a function. I'm just making this up, guys. And you just see this. It says, let me think of one. X squared minus 9 over x minus 3 for x cannot equal 3. And then I'm going to play 5 when x equals 3. Okay, that one has a hole. I don't plug in that hole. So this one is not continuous at 3. Travis, how do you know just by looking at it? I drew the difference of squares on purpose. X minus 3, x plus 3. X minus 3's cancel out. So this function behaves like x plus 3 everywhere. And what's 3 plus 3? 6. But look, when x equals 3, it equals 5. So I don't plug in that hole. I guess you guys are visual, so let me draw the graph. Because I know you guys are just looking like, I can't tell. So this graph here, this one that I drew in blue, looks like this, guys. Let's see, x plus 3, 3, and looks like that. And I have a hole at 5, so it looks like this. Am I continuous? No, but what if I did this? What if I change that to a 6 at x equals 3? It would plug the hole back in, this is no longer there, and now is f of x continuous? By definition, it is. It's a trick question because, I did it in pieces, but by definition, yeah, it's continuous. Does that make sense, guys? Well, if it's not the same, that means the limits don't even...
Oh, basically, they're just saying, you can't have a vertical asymptote or a...
Yeah, vertical asymptote, hole, or jump discontinuity, pretty much. Cool or not cool? All right. There are 4 forms of discontinuity. And I don't know why I only drew... I don't know what I was thinking. These notes are from last year. I didn't revamp them much. I took away some questions, actually. I'm trying to think why I only put 1 in there. I'm pretty sure that I meant to type all 4, like to put them in, but for whatever reason I just put 1. Or maybe it just didn't come out. Anyways, let's just go right into it. There are 4 forms of discontinuity. This one right here is called an oscillating discontinuity. Can you take a guess why it's called that? It's just going back and forth. It's just going back and forth. Where are you discontinuous? At 0. And this graph doesn't show it very good, but if you were to type this in the calculator in the middle, it just looks like... It looks like all super squeezed in. So, but it doesn't show it very good, that picture there. It just goes back and forth, and you can't tell. You know what I mean? Like at 0, you're undefined. You can't tell. It's bouncing too much. This is not as common. The most common one is something called a jump discontinuity. Jump discontinuity. And that looks like this. I have a curve. Maybe this one is solid and the other one is open. And you have a jump. There's your jump right there. Do you guys see that jump? What do you think they call the vertical asymptote? Something discontinuity. What word do you think they use? Maybe that might be a word, actually. It starts with an I. Isometric. Let's make this one go down. Infinite, yeah. Infinite discontinuity. It sounds nice. Infinite discontinuity. Why is it infinite? Because you can approach positive infinity or negative infinity. Infinite discontinuity. The discontinuity goes forever. Cool? So if someone's being like, when you're talking to your friend and they just keep going and going and going and going and you're mad at them, like, infinite discontinuity. You're being such an infinite discontinuity right now. All right. When someone, yes. I don't have to fill in. If I wanted my domain to be all row numbers, I would fill in one of them so my domain can be all row numbers. You know what I mean? The last one, not to be confused for oscillating, there's the simplest one. What do you think that's called? It's a hole, but what's the official name? Oh no, not hole discontinuity. I think I've heard someone say it. There it is. This is called a removable discontinuity. This is a technical term. So when you go chat with a professor, instead of calling it a hole, I mean, he'll understand. He or she will understand if you say hole. But you could just say removable discontinuity, and they will be like, this person is speaking my language. And why do they call it a removable discontinuity? Because, yeah, it's just one pixel, guys. You can make a removable discontinuity continuous if you fill in that pixel or that one singularity. Yes.
Would the jump would that be, would it still be a jump one if the hole was still?
No. Well, yeah. Yeah, but then it wouldn't be a function because it doesn't pass the vertical line test.
Gotcha. Okay. Yes.
She asked if I filled in this hole over here, if it would still be a jump. I mean, I guess technically it would be, but for it to be a function, it has to pass vertical line test, and you can't have two different x values for you know what I mean. Like the x's can't repeat for your domain. What's up? You can have two holes. That's fine. That's still a jump. Any other questions, guys? Are we good? Okay. All right. Let's look at this graph here. We're identifying the type of discontinuity. Oh, are you ever discontinuous at an endpoint? No. That's what this was trying to tell you right here. Do you guys see that? So if I chose to have endpoints over here, let me have endpoints. A and B. That's all it means. As you can see, limit as x approaches a. There's only one way to approach a from the right-hand side of this function, and that equals f of a. And limit as x approaches b. There's only one direction for b from the left-hand side, and that approaches f of b. So endpoints are continuous by definition. Cool? Okay. Any questions on that? Okay. So here we go, guys. Find where the graph is discontinuous. Where am I discontinuous? At 1 for sure. And what type of discontinuity is that? That's a jump. Jump discontinuity. Where else? 2. What type of discontinuity is that? Perfect. Removable. Is there any other discontinuities? I think that's all I see. Is that all you guys see?
Is removable like
It's a hole. Removable discontinuity is a hole. Cool.
So you know how for x equals 1, you circle like where it jumps? For x equals 2, you just circle that one right there.
If they ask you where are you discontinuous, you would say at 2, 1. And at x equals 1, there's a jump. So you have a hole at 2, 1. All right, look at example 2. I think we're ready now. We're getting really close to being able to do free response questions. We're getting really close. Here's our first one. Y'all ready? Example 2. Consider the function kx squared plus m for x less than negative 2, 4x plus 1 for x is between negative 2 and 3, and kx minus m for x greater than 3 to answer the question below. Letter A. What two limits must be equal for g of x to be continuous at x equals negative 2? Yeah. What I guess maybe I should say what two expressions must be equal for x to equal negative 2 to be continuous? So the first two? So how do I say it? Limit as x approaches negative 2 from the perfect from the left of g of x. So when I say left, we know that we're talking about this one right here, right? From left.
Is it also because of the second one, negative 2, that's always left?
Yeah, x less than negative 2, that's to the left. And then the middle one, x is between negative 2 and 3. So if I'm looking at 2, that I'm approaching from the right on that one. From left of x equals negative 2. And that must equal the right, so negative 2 from the right of that same function. So if we're being specific, I must have limit as x approaches negative 2 of kx squared plus m equal to the limit as x approaches negative 2 from the left, by the way, this one from the right, of 4x plus 1. Does that make sense? And of course, this also has to equal g of negative 2, which has to equal the 4x plus 1. Yes, ma'am.
For the limit for
Oh, I'm approaching negative 2 from the right. These two must match. These two right here must converge on the same y value at negative 2 for it to be continuous. Because it's a piecewise function. So when this one stops, the other one better start.
And it can't be the other one because the other one.
Well, the other one's for 3.
Yeah.
Right? So these two right here, expressions, at negative 2. At negative 2, I stop drawing the kx squared plus m, and I start drawing the 4x plus 1. So at negative 2, those better have the same y value if I want to be continuous. Does that make sense? How do you spell? So I don't know how this graph looks, not yet at least. I have a parabola, and it looks like this. So whenever this parabola stops, I'm going to pretend it looks like that. The other one, which is a linear line, that one better start. If they don't touch at that same y value, it's not continuous. If I have something like this, a parabola, and well, let me draw it better. If I have something like parabola and then a linear line like that with a gap in there, that's a jump. I'm not continuous. I want it to be continuous, so I better be converging at the same y values. Left, then it's coming from the right. Are we okay, guys? And really, man, I worded that question wrong. What two limits must be equal? I mean, I guess those two limits must be equal, but it also has to equal g of negative 2 for it to be continuous. But good thing we caught it on video and we'll upload it. And so the YouTube haters won't be haters. Okay, are we okay so far, guys? What two limits must be equal for g of x to be continuous at x equals 3? At x equals 3.
So it's kx minus x, the last one for sure.
Uh-huh.
And then I
Equal.
guess the middle.
Yeah, because that's the one, the middle one is between negative 2 and 3, right? So limit as x approaches 3 from the left, which is 4x plus 1, must equal limit as x approaches 3 from the right, which is perfect. Was it minus? Yeah. There it is. How do we feel? All right. So now let's see what it says. Determine the values of m and k so that the function is continuous everywhere. All right, let's start. So I'm looking at the first one. So these two must equal each other at negative 2. Yes, ma'am. Yes, ma'am. So here we go. I'm going to write, what am I going to write? K, yes. Oh, yeah, there is. They're going to announce it when it's our turn. M times, they said they were going to announce it. They were going to call us out. They're going to try to do it during advisory for high school, I think, or something. Guys, I backed up too much. Okay, you guys tell me. Kx squared plus m. So, this is wrong. What was my equation for the negative 2 from the left-hand side? Okay, so my value for x is negative 2 squared plus m, and that better equal what?
Oh, okay, so you're just plugging in values.
I'm evaluating my limit.
Oh, and it's equal to
4 times negative 2 plus 1. I'm evaluating the limits, guys. Limit from the left better equal limit from the right. At what y value? At negative 2, right? So all I'm doing is plugging in a negative 2, guys. Are we okay so far? All right, negative 2 squared is? So 4k plus m better equal, what's 4 times negative 2? Plus 1. So there's my equation 1. Now let me do equation 2. So I'm going to come over here. Equation 2 is at what x value? Or I guess, yeah, at 3. So I'm evaluating my limits at 3, guys. So here we go. 4 times 3 plus 1, and that better equal what? K times 3 minus m. All right, so here we go. So 4 times 3 is what? 12 plus 1. 13 equals 3k minus m. That is your equation 2. I think, yeah, we got enough. We got enough, guys. So let me write a system here. So now it's just algebra. So let's see. Here's what I'm seeing. I'm seeing a positive m. I'm seeing a negative m. Can't I just stack them? Yeah, let's stack them. So let me choose a neutral color. So here we go. 4k plus m equals negative 7. And 3k minus m equals 13. I stacked them. I'm just going to add them. When I add, the m's cancel out. And then 4 plus 3, 4, 5, 6, 7. So 7k equals the difference between negative 7 and 13. Or 13 minus 7. Positive, yeah. So divide by 7. What does k equal? Now that I know what k is, can I solve for m? Yes, it doesn't matter which one you use. I'm going to use a 3k. 3 times 6 sevenths minus m equals 13. So what's that? 3 times 6 is 18 over 7 minus m. Oh, I should have used the other one. Oh well. Move the n to the other side, the 13 to the other side. 18 over 7 minus 13 equals m. What's 13 times 7? Yeah, I shouldn't have done that one. I already chose that one. So 18. So m is equal to negative 73 over 7. Yes. Oh, I just solved for the letter m. I can just move the when I'm getting a letter by itself, Miss Parker. So you see how I'm trying to get m by itself? I just moved it to the other side and it turned to a positive m. And I moved the 13 to the other side and it turned to minus 13. I mean, I could have moved this to the other side, but then I had to divide by negative 1. I didn't want that. Yes. Yeah, go ahead. I thought it was easier. The algebra is what's gonna hurt us, I think. Any other questions on this, guys? What do you guys think?
I think I'm getting it slowly. I'm just not getting it quick.
No, you're good. You're good, miss. Let me do a side note. All right, Parker, if I had this, 4 minus x equals 5, in my brain, I think it's easier to do this and do that. So in my brain, I think 4 minus 5 equals x is easier. So I go negative 1 equals x, so I just say x equals negative 1. I think it's less, but you're more than welcome. There's nothing wrong when the readers are going to read it. If you want to go minus 4, negative x equals 1, divide by negative 1, divide by negative 1, x equals negative 1. If you want to go that route, perfectly fine. It doesn't matter what route, as long as you understand it. No problem. I always look for ways to turn the variable positive. And if I can turn the variable positive, I try to do it immediately. If not, you can always just keep going, leave the x there, move it to the side, and then divide by that negative 1. That's fine too. Did I answer your question? Yeah, ask, miss. I can't read minds. So just ask, and then if you don't like the first answer, ask again, and then ask again. And eventually I'll get the hint and be like, oh, okay. And then I'll do an example, So, any other questions, guys? Okay. I think we have enough. Do we have enough energy to do one more? Okay. So this one is coming. We haven't asked this question yet. I don't. Is this from quiz? No, it's on the continuity quiz. So it's not. We're not assigning it yet because we're not experienced enough yet. But here we go. You guys ready? It says, given the function f of x equals blah, define the function f of x at 5 so that it becomes continuous at 5. So the only way we can make this continuous, the only way, is if I have a removable discontinuity at 5. If I have an infinite discontinuity, you cannot make it continuous because you have a vertical asymptote. Does that make sense? So I need to make sure that this really, in fact, has a hole at x equals 5 and not an infinite discontinuity, not a vertical asymptote. So now the question is, Chavez, how do we do that? So the way we do that is we're going to evaluate this like so. Limit as x approaches 5 of the square root of x plus 4 minus 3 over x minus 5. Chavez, I don't understand the method that we're doing. Well, I'm trying to see if this limit exists. If I have a limit, that means I have a hole. Does that make sense? Because if I have a limit at x equals 5, if you get a number, that means you're converging somewhere.
Oh, okay, because you have a hole and a limit.
Correct. Now, if I get does not exist, if I do all my algebra and I get does not exist, then I have a vertical asymptote and there's nothing you can do about it. Cool? All right. So when we have something like this, what does your brain tell you that we should do? Similar to what we did for trig. You see something hard in the top. I mean, I don't know, maybe you think the x minus 5 looks tough too. But you see something ugly in the top, and in your brain, hopefully you have enough experience, it's telling you to do something. Multiply by what? By the conjugate.
Yeah, conjugate. Yeah.
We're going to multiply by the conjugate. So anytime, hopefully, and this comes with experience, guys. If we were to give you this question as a freshman, you probably didn't have enough experience. And because of the pandemic, you haven't done enough problems, like a whole bunch, like you would in years past. But hopefully now we're getting back into the rhythm, and you're starting to feel like, oh, it feels like I should multiply by the conjugate. So that's what we're going to do. Square root x plus 4, and instead of minus 3, I'm going to write what? Plus 3 over square root x plus 4 plus 3. Relax. This is like the difference of squares. It's like the difference of squares. So you don't have to FOIL or do the whole distribution in the numerator. You can just do this. This times this. Does the square root go away? Yes. We're going to write limit as x approaches 5 of x plus 4. I like to put a parenthesis in case there's a number on the outside that we're going to do. And then do this. Negative 3 times 3. What's that? Minus 9. All over on the bottom. Don't bother distributing the bottom. Leave it as x minus 5. And then parenthesis again. Square root of x plus 4 plus 3. Are we still okay? We drop the parentheses in the numerator. So limit as x approaches 5. Like Snoop Dogg says, drop it like it's hot. So x plus 4 minus 9. Positive 4 minus 9 is? Negative 5. So I just write x minus 5. And look at that. We got lucky. I mean, I wouldn't call it luck, but is there something we can cancel? What can we cancel out? Now that we canceled out the x minus 5, now can I do direct substitution? Yes, we can. So now that I'm evaluating my limit, I no longer have to write the word limit. 1 over, what's this? Well, I guess let's plug it in. 5 plus 4, and then on the outside plus 3. So 5 plus 4 is 9. So what's the square root of 9? So 1 over 3 plus 3, which is, now that's my limit. So we just got to do one last thing, because we haven't answered the question yet. We just found a limit. So I'll wait for you guys to catch up. Oh, I dropped the parentheses, and I did 4 minus 9. All right. Don't worry. We're almost done. Yeah. Yes, ma'am. On the exam?
No.
this one. Is this some?
Yeah, you can do that on that one too. You could also, if you recognize the bottom, that's a difference of squares. Square root of x times square root of s is s, and 4 times 4 is the top.
Okay, so
you
I
see it?
can do that.
So in the bottom, you can write square root of s minus 4 times square root of s plus 4. Do you see it? Because square root of s times square root of s is s, and 4 times 4 is 16. But you can also do your method, multiply by the conjugate on the top, and you'll get the bottom.
Okay.
All right, last thing, guys. This is my answer, but you got to tell it. So look what it says. It says, define the function f of x at 5 so that it becomes continuous at 5. So all you got to do is do this. F of 5 must equal what? Yeah, there it is. If you make f of 5 equal to 1/6, you are continuous.
Because that's where the discontinuity.
That's where the hole is at.
So you would just put a thing there.
Yep, 5, 1/6. That's the hole is at 5, 1/6. So if I write f of 5 equals 1/6, you're plugging the hole. Yes. Castillo or Arispe? Well, I know the hole's at 5 because I actually got a limit, like a number. So right now I have a hole. The hole is at 5, 1/6. Now I want to plug in that hole. How do we plug in that hole? By writing f of 5 equals 1/6. If there's no limit, there's no hole. You all right, Moreno? You look like you're okay. All right. We have one more concept, and we're looking at this here, and it says Theorem 8. So obviously, I took this from some textbook. If you're wondering what textbook I took it from, it was a Demana 3rd edition, which is the textbook that our school uses. So technically, I'm not like, any rules because we're supposed to be using a textbook, right? And so read that and see if it makes sense to you guys. Does that make sense? No? Nothing, kind of? All right.
Yeah, the first part makes sense. But in other words,
The continuous? Oh, it's continuous. No, I thought it was funny, but maybe it's not. All right, so here's what they're trying to say. So we're going to, I have this example on the bottom, but I don't like it. I'm just going to create a new example. So let's say I have a graph, and I want to know if I cross the x-axis. So let's say that I call this function f. And all I know right now is that I have a coordinate at 2, -3, and I have another coordinate at 5, 2. If I tell you that f of x is continuous, are we listening right now, guys? If I tell you that f of x is continuous, did I cross the x-axis? Yes, for sure. How many times? You do not know. It could have done it once. It could have done it many times. It could have gone. We don't know how many times it crossed, but we know for a fact we crossed at least once. That's all it means. So that's all it means. So what they did in this picture here, we have some value, it's f of a. We have some value, it's f of b. And we cover every single y value between f of a and f of b. Do I go a little above? Well, this graph does. Do I go a little below? Well, this graph does. But we don't, let's say they were to delete all this, and they were to tell you, is it possible that this graph equals, some number down here? Well, yeah. If it's continuous, I cover all the numbers between f of a and f of b. Does that make sense? And there's actually a very perfect, let's do an example, and then I'm going to show you guys some Delta questions on how to answer them correctly so we can have the right idea. So look at example 5. It says, can the IVT, by the way, IVT is an abbreviation for Intermediate Value Theorem, be used to show that there is a solution for the equation f of x equals 0, that means that I cross the x-axis, on the interval 1 to 2 if f of x equals blah. Give an explanation why. All right, here's how you're going to do it. You guys ready? I'm going to find out what f of 1 is. So I'm going to write f of 1 equals 3 times 1 cubed minus 5 times 1 squared plus 1 minus 3. And I'm going to see what that is. That's 3 minus 5 plus 1 minus 3. So I see negative 4, but let me know if I'm wrong. I'm wrong very often. Are we okay? All right, now let's figure out what f of 2 is. 3 times 2 cubed minus 5 times 2 squared plus 2 minus 3. Let's see, what is that? 3 times 8 minus 5 times 4 minus 1. So 8, 16, 24 minus 20 minus 1. I get 3. Do you guys get 3? Okay, so now check this out. If at 1 I was at negative 4, and if at 2 I was at positive 3, do I have an x value somewhere between 1 and 2 in which f of x is equal to 0? What do you guys think? They're telling me it's continuous.
Yeah, so you're gonna go from negative 4 to 3.
Perfect. So I do. I'm going to go, there exists a value c, and I'm going to tell you what c is. This is how you would write it on any exam, not just the AP exam. There exists a value c such that f of c equals 0 since what? Since f of x changes signs from x equals 1 to x equals 2. Does that make sense to you guys? Maybe it doesn't. There's other ways to say it. You know what? Maybe we're not that advanced. Don't write that part down because we're not advanced yet. Just scratch it. You don't have to erase. You can just... there exists a value c such that f of c equals 0 since f of 1 equals negative 4 and f of 2 equals 3, comma, indicating that somewhere between x equals 1 and x equals 2, somewhere between x equals 1 and x equals 2, comma, f of c was 0, period. I think that makes sense, but I don't know if it makes sense to you guys. Let me read it. There exists a value c such that f of c equals 0. Oh, and I guess I got to tell you where c is, right? C is between 1 and 2. C is between 1 and 2. Do we know how many times I crossed it? No. I mean, I guess if you graph it, you can, but no. But do we know that we definitely crossed the x-axis? Yes. How do we feel? What's up? Yes. Correct math is correct math. You can write complete sentences out. Let's do another one really quick. I'm just going to log in. I'm going to pause this. No, I'm going to